So imagine a spring, got some mass on the end of it, and I stretch the spring some distance x. So that means there's going to be a force back. So that means as long as the spring is to the right, there's going to be a force to the left. And so this mass will be accelerating back this way. Then it reaches the equilibrium point, but it's been accelerating the whole time, so it's still moving, so it's going to overshoot and compress the spring. Well, if it compresses the spring, there's a force to the right. And so as it's pushing to the right, it's going to push this way until it reaches the midpoint. It's still moving, so it's going to overshoot and get over to the right. When it's to the right, there's going to be a force pushing back to the left, and it's going to sit here oscillating back and forth. So this is going to be oscillation. So we want to describe that oscillation somehow. So we know that the force equals ma. Well, we also, the force is equal to minus kx because of the spring that's doing it. So we can write ma equals minus kx. So a equals minus k over mx. So the second derivative of x, respect to time, equals minus k over mx. So what we have here is an equation in x and we want to solve that. Okay, now this is a differential equation. So you have a course you're going to take on differential equations. And so what we want to do is, how do we solve a differential equation? So I want to find some x equals something. So I say, okay, the way you do this, the way you solve differential equations, when I was a student, I struggled trying to figure out how to solve differential equations, and so it was about halfway through my DiffEQ class in which I realized, oh wait, it's educated guessing. What you do is you kind of guess a solution, try it, see if it works, and then modify it until it works. And the professor said, no, that's not how you do it. And I said, well, what do you do? And he said, well, you make a postulate. And I said, well, isn't that like an educated guess? Yeah, anyway. So what we're going to do is, the k over m is constant. So let's imagine solving a simpler equation here. And say, what can you think of if you take the derivative twice, you get negative of what you started with? Well, that would be the case if x equals sine or if x equals cosine. Okay. That would do it. Okay, we're taking derivatives for t. Okay, if x is sine, two derivatives is negative sine t. If it's cosine, two derivatives negative cosine t. And so that answers it. If I multiply it by a constant, that doesn't change anything. It still is the same. Okay, and so that's a pretty good guess. Okay, in fact, you know, if I actually take this t right here and add something to it, when I take a derivative, it doesn't change anything. So all that's all the same stuff. Okay, now the problem though is, and so normally if we stretch a spring, it starts off as non-zero, so I'm going to guess cosine right here. Okay, and so what I would do is I'm going to guess that the answer is some a cosine omega t, and I can put some kind of like plus phi in there. So a derivative dx dt equals minus a omega sine omega t plus phi, and a second derivative is minus a omega squared cosine omega t plus phi. But if this is x, then this means this is minus omega squared x. Okay, and so if I had said up here that the second derivative of x respect to time was minus k over m x, and if x equals a cosine omega t plus phi, then that means that omega squared equals K over M. Okay, so omega equals square root K over M. So that's the angular velocity right there. Okay, and so with that, we have a solution. So this would be a solution to that differential equation right there. And so the A is the amplitude. That's how big of an oscillation it is. Omega is the angular velocity. Well, we know if we go one complete cycle, so if it starts here, I stretch it, it goes back, that's one cycle. That's the time it takes to go through one cycle is a period. So if T is equal to 1 period, then that means that omega T, which is omega times T, has gone through a cycle of 2 pi. So that means the period is 2 pi over omega, or in other words, the period is 2 pi square root M over K. So that tells you the period of oscillation. And so now we got a spring with a mass on it. We know that if we pull it out of position, it's going to repeat motion like this. A is how far we started out of position. So A is the amplitude of the oscillation. Now, if I just pull and let go, then that means that phi is 0. So this is just cosine omega t. If, on the other hand, I start my timer at any other time, so in other words, if I don't start my timer right at the peak, in other words, if I pull it out and then toss it this way a little bit, it goes a little further, then that would be the case in which phi is not 0. So phi we call the phase factor, or sometimes the phase angle. Basically, the only thing that does for you, it tells you the adjustment you make to the equation for not starting at the extreme. And that's the only thing that it does for you. And then omega is the angular velocity, and so that gave us the period, which is 2 pi square root M over K. Now, this can be described with a sine or cosine. Sine and cosine are called harmonic functions. We are describing this motion with just one harmonic function, so we call this simple harmonic motion. My books just abbreviated SHM. Okay. Or a mass with a spring is a simple harmonic oscillator. And we can just abbreviate that SHL. So this introduces the idea of oscillations, simple harmonic motion, and that's basically most of the key part of chapter 15. Now we can go one step further than that and talk about energy in here, but let's do a couple of examples first of all.